Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to chemistry class with chapter 6 solids. Today we are going to discuss what are solids, types of solids, that is crystalline solids, its examples and applications, amorphous solids, examples and applications of amorphous solids, comparison of crystalline and amorphous solids, example of calcium carbonate and properties of crystalline solids. Today we are discussing just geometrical shape, melting point and cleavage planes as properties of crystalline solids. Next properties will be discussed in the coming lecture. Let us start today's topic. First of all, what are solids? Solids, as you people know, that solids have definite shape and volume because the average distance between the molecules or atoms remains constant and they do not change with time. Arrangement of molecule inside a solid differ from one another. That is, one type of solid have some arrangement of molecules, some specific arrangement of molecules as compared to other solid. On this basis, on the basis of arrangement of particles, we classify solids into two categories: crystalline solids and amorphous solids. Crystalline solids. The word crystal is derived from ancient Greek word kristiolis, which means both eyes and crystal. Crystalline solids are firm and hold a definite and fixed shape and are rigid, incompressible. They generally have geometrical shapes and flat faces. The arrangement of particles in a crystalline solid is in a very orderly fashion. These particles arrange in a repeating pattern of the three-dimensional network. This dimensional network is known as crystal lattice, and the smallest unit of a crystal that can represent the whole crystal lattice is called unit cell. From X-ray of a crystal, this arrangement can be seen. The spaces between the atoms are very less due to high intermolecular forces that results in high melting and boiling point of crystalline solids. The intermolecular forces are very uniform throughout the structures. Crystals have long range order, which means arrangement of atoms is repeated over a great distance. Examples of crystalline solids are diamond, metals, salts like NaCl, copper sulfate with 5 water molecules, and calcium carbonate. Next are applications of crystalline solids. Diamond is the most decent example of crystalline solid that is widely used in making beautiful jewelry items and in some mechanical instruments as well. Just like on the tip of drilling machine, diamond piece is used. Quartz is also used in making watches and clocks. Many crystalline solids are used as a raw material in many industries. An important crystalline solid is sodium chloride. Our food is incomplete without this article, without this ingredient. It is the main ingredient of our all food. Our food is tasteless without this. So it is the main use of crystalline. It is the most important crystalline solid. This is picture of crystalline quartz with formula SiO2. The next are amorphous solids. The word amorphous has originated from Greek words a, that means without, and morph, that means shape. Together, it means shapeless. It means it has no definite shape. Amorphous solids are rigid structures, but they lack a well-defined shape. They don't have a geometrical shape and they are non-crystalline. They don't have sharp edges. This variation in characteristics of solids occur due to the arrangement of their molecules. The particles of matter do not form three-dimensional lattice structures that we see in crystalline solids. Some naturally occurring amorphous solids have impurities that prevent such a structure forming. They have short order arrangement of molecules. Amorphous solids break into uneven pieces with irregular edges and they don't have any distinct arrangement or shape of molecules, so they cannot be identified by their shape as crystal. Examples of amorphous solids are glass, gels, plastics, polymers, candle wax, rubber, chocolates and cheese, butter, glass. These are the some important examples of amorphous solids. This is the structure of a glass. Applications of amorphous solids in our daily life. The most important amorphous solids is glass, that is widely used in packaging for food jars, cosmetic boxes, and soft drink bottles. Also used in making tableware, that is utensils, and in constructions of buildings, windows, lighting, and shelves, etc. Rubber is mainly used in manufacturing of tires, footwear, ropes, camp cloths, and used as a raw material for several industries. Use of polymer can be seen in manufacturing of pipes, medicines, and as a raw material for many other factories. One of the most important amorphous solid is amorphous silicon, that is considered as the best photovoltaic material to convert sunlight into electricity. That is the emerging technologies nowadays. That you can see, this is a cell that captures sunlight and further it is converted into electricity by this procedure. Amorphous silicon is used in this process. Now our next topic is comparison of crystalline solids and amorphous solids. First of all, we see geometrical structures. Amorphous solids have irregular geometry or structure, while crystalline solids have regular geometry or structure. Arrangement. Amorphous solids have atoms that are arranged in indefinite manners, while in crystalline solids, atoms have arranged in a well-defined manner. Intermolecular forces. Amorphous solids do not have uniform intermolecular forces, while crystalline solids have uniform intermolecular forces between them. Cleavage pattern. Amorphous solids cleave into uneven parts with ragged edges, with crystalline solids cleave along particular points and directions. Melting and boiling points. Amorphous solids do not have sharp melting or boiling point, so they can be molded into different shapes, while crystalline solids have sharp melting and boiling point. Amorphous solids are less rigid, while crystalline solids are more rigid. Amorphous solids show isotropic properties, that is, they exhibit same value of any physical property in any direction, while crystalline solids have anisotropic properties, that is, their value changes. Amorphous solids are known as supercooled liquid, while crystals are also known as true solids. Amorphous solids do not have any water of crystallization, while crystalline solids have water molecules as part of the crystal, which are known as water of crystallization. Like copper sulfate, CuSO4 have 5 water molecules which are known as water of crystallization. These water of crystallization evaporates on heating and the hydrated copper sulfate becomes anhydrous, and definitely their color also changes from blue color to white color. The next is effect of heat. Amorphous solids soften on heating and becomes mobile on over a wide range of temperature, while crystalline solids does not show this property. Amorphous solids may be compressed to some extent, but crystalline solids are totally incompressible. Amorphous solids have no further classification, while crystalline solids can be classified into 7 more systems. Amorphous solids cannot be converted into crystalline solids. Crystalline solids can be converted into amorphous solids by heating them and then cooling molten liquid rapidly. Examples of amorphous solids are rubber, glass, plastic, cement, and paraffin. Crystalline solids have examples like curds, calcite, rock salt, sugar, mica, and diamond. Now we consider an example, that is calcium carbonate. You people have heard its name. Calcium carbonate is a solid. Now, either it is a crystalline solid or amorphous solid. It depends on the basis, it depends on the arrangement of particles in calcium carbonate. It exists in crystalline solid and amorphous solid. In crystalline solid, it exists in the form of marble, and definitely you people are well aware about marble, and you people know it is hard enough. Marble have regular arrangement of particles. long range order of particles, sharp melting points, and they show anisotropy. Because of these properties, it is a hard crystalline solid. Marble is hard crystalline solid. Now come towards its amorphous solid, that is the chalk, which is soft. It is soft because of irregular arrangement of particles, short range order of particles, and broad melting points. It also shows isotropic behavior. So here you people discuss that chalk and marble both are calcium carbonate, but one is very hard and other is very soft. This hardness and softness depends on the arrangement of particles in it. Therefore, marble is hard enough and chalk is very soft. Next is properties of crystalline solids. Crystalline solids show number of properties like geometrical shapes, melting points, cleavage planes, habit of crystal, crystal growth, and isotropy, symmetry, isomorphism, polymorphism, allotropy, transition temperature, and many more. In today's lecture, we just covered these properties. First is geometrical shapes. The atoms, molecules, or ions are arranged in a very ordered microscopic geometrical shapes in crystalline solids. In crystalline solids, the orderly arrangement of atoms, ions, or molecules are repeatedly itself periodically over the whole crystal and extend over a large volume of the crystal. That is why all atoms, ions, and molecules are arranged in definite geometrical order, forming three-dimensional crystal lattice. This is three-dimensional crystal lattice of sodium chloride. And here you can see that one unit is repeating multiple times, and it have a large range order of atoms, molecules. NaCl is cubic in nature. This structure is known as cubic. Next is melting point. Crystalline solids have sharp melting point. Why they have sharp melting points? Because crystalline solids have very strong and equally strong bonds among all atoms, molecules, or ions. These forces are very strong and they hold these crystals together. These forces may be dipole-dipole interactions, London dispersion forces, or hydrogen bonding, or maybe it van der Waals forces. What happened when we heat a crystalline solid? When a solid is heated, its atoms, molecules, or ions present in it start vibrating at a high frequency, and during this vibration, they transfer their kinetic energy throughout the solid. At the melting point, their vibrational energies become so much that they leave their fixed position simultaneously and finally they convert it into a liquid. For example, NaCl is a crystalline solid and it has melting point 801 degrees centigrade sharp. That is, it has a very sharp melting point. This is long range order and it is responsible for sharp melting point of NaCl. Next is cleavage plane. What is cleavage? Cleavage is basically the term used for breaking off large molecules or large items into smaller pieces with identical size and shape. That is, breaking up of large crystal into smaller one with identical size and shape. It is called cleavage. The plane which contains the direction of cleavage is called cleavage plane. The crystalline solids can be cleaved along a definite shape or plane. For example, nickel sulfate with 6 water molecules can be cleaved easily to its parallel surface. Sodium nitrate and calcium acetate. Here its formula is CH3COO2Ca, and it can be cleaved easily parallel to the surface. Sorry, here 2 is missing. Mica can be cut easily parallel to the layers. Here is a short video for you people that show you its cutting. This sorry, it is a picture, and this show how it is converted, how it can be cut parallel to the surface, and finally it is converted into sheets. And I hope you have enjoyed the lecture. The last is assignment. Explain crystalline solids in detail. Differentiate between crystalline solids and amorphous solids. Amorphous solids show isotropic properties. Comment on it. Crystalline solids exhibit cleavage property. Explain it. Amorphous solids are called supercooled solids. Why? Crystalline solids possess special geometrical shape. Explain the statement. What changes occur when a solid is heated and it changes into liquid? I hope you have enjoyed the lecture. Please raise your questions or any query if you have. Thank you and have a nice day. As you people know that mica can be cut easily parallel to the layer. Here is a short video for you that shows you how mica can be cut parallel to its surface. As you people can see, it is cutting parallel. This mica is cut parallel to the surface, and it is very easy to cut parallel to the surface. It can be cut very easily parallel to the surface because of arrangement of its particles. These arrangement of particles basically allow its parallel cutting, and you can see that how easily it can be cutted along its parallel. I hope you have got the idea. Thank you.